Hi everyone. Today I'm going to talk about the lab that we're going to be working on this week, and this lab is called the Types of Reaction Lab. And this is actually a fairly straightforward lab. Unlike other labs that you've been working on, this is going to be a qualitative lab, so you're only going to be observing and writing down signs of chemical reaction. So we know that a chemical reaction has occurred when we observe one of the following changes: temperature changing, color might be changing. You might see a gas coming out of the as a result of the reaction. So you see some kind of bubbling. Precipitate might form, or the metal you put in might change its appearance. Maybe it becomes less dull or more dull, one way or the other. So if you see one of those changes, then you know that a reaction has happened. So you would write a correct balanced chemical equation for that reaction that you observe. And then you're going to try to predict what products they're forming. Now, there's some reactions that you might not know what the products are. So in that case, you can just go online or go to your textbook to try to determine what the products are for those reactions. Now, all the different types of reactions that we talked about, which is decomposition, combination, combustion, single displacement, double displacement, as well as precipitation and acid-base reactions, all of those would be observed in today's lab. So you'd have a chance to look at all of them. Also note that for the double displacement reaction, you're going to have to write net ionic equations. So you want to look back in your notes if you haven't done this for a while. Look back and try to remember how to write those types of equations. Now I do want to spend a little bit more time talking about part of the lab report that asks you to build a partial activity series for various metals and hydrogen. Okay, so activity series, as you remember from topic 4, is basically a list of substances in being ranked by their activity. And what we mean by that is an element or a substance that's more active is put on top of that list, and then the ones that are less active are put at the bottom of that list. And these series is actually relevant when you're trying to predict single displacement reaction. A more active element or metal can displace those that are less active. So in other words, if you have a reaction in a single displacement reaction, that can only happen if you have a more active metal reacting with a less active one. Now, what the lab wants you to do is actually to use your experimental observations and build a partial activity series. So in other words, as act as if you don't know that there's an activity series and you're the first person to try to figure out what is the relative activity of the metals you're using and hydrogen, and try to rank these activities in your own activity series. How's that going to work? Well, let's try it out with an example. So let's say you have a metal A, and you're trying to determine whether that metal A is more active or less active than another element B in this case. So you mix A with a compound that contains B in it as the cation, and you want to see if there's a reaction happening. So there's two possibilities. You can either have a reaction or you can have no reaction. Let's talk about the possibility where there is a reaction. If there's a reaction, so let's say you notice, temperature changing or bubbling or something is going on, okay? So you see that the reaction is happening. The reaction happens, that means A displaces B, right? So your product looks like this, AC plus B. Now, if you have a reaction, then your conclusion is very simple. A is more active than B, right? Because we know from our previous discussion, unless A is more active than B, the reaction will not happen. So in this case, we can say in your activity series that A must be more active than B. What happens if you don't see anything happening? You mix the two things, you don't see anything happening. First thing you're going to do is you're just going to write it like this. You're going to put a slash across that reaction arrow and say that no reaction occurs. Now, if no reaction occurs, that of course tells you that A is less active than B in this case. Okay. Now things get a little bit more complicated when we're dealing with hydrogen. The reason is because hydrogen can exist in two forms. It can exist as an acid, for example, in HCl, HNO3, and it can exist as water in H2O. Now it turns out that when H exists as an acid, it reacts with more things compared to when H exists in water. Here's what I mean. It's possible, for example, that you take a metal X and you mix it with water and you see no reaction. And then you mix it with HCl and you see a reaction producing hydrogen gas and metal chloride. So then how would you interpret this result? Because when you look at the first one, it seems to say that X is less active than H because there's no reaction. But then the second one seems to indicate that X is more active than H because there's a reaction. Okay, so in this lab, we're going to make it real easy. If we see an example like the one I just showed you where it reacts in one case, it doesn't react with the other form of H, we're just going to say it's more active. So anytime you see any reaction at all, whether it's just with HCl, with the acid, or with both of them, you're going to say that the element is more active. The only time you say the element is less active than H is when there is no reaction with both forms of H, with both the acid and the water form. It's a quick example to show you how this works. Let's say you take manganese and you put it in water and you see a reaction. And then you take copper, put it in acid, and you don't see a reaction. The question is, which metal is more active, manganese or copper? Well, the fact that manganese can react with water implies that manganese will also be able to react with acid, because remember, acid is the more reactive form. So then manganese must be a more active metal compared to H. Okay, so that's the first thing you need to keep in mind. The second one is you look at copper with HCl. Well, HCl is a more reactive form of H. The fact that copper cannot react with HCl tells you that copper also will not react with water, in which case copper must be less active than H. So manganese is more active than H, copper is less active than H. That tells you that manganese must be more active than copper. So here's that conclusion that I just discussed, that manganese is more active than copper, and I found this conclusion by comparing the activity of each of those elements compared to H.